All right, hello class. We're going to go over chapter 2 in journal 1. Okay, and the title of this chapter is Differentiation, which just means to take a derivative. And at this point from chapter 1, we only know one way to take a derivative, which is with the limit definition of the derivative. So in chapter 2, we're going to learn ways to avoid that limit definition that are much faster, easier ways to take a derivative. Now, why do we want to take a derivative? We saw a few applications at the end of chapter 1, in particular with the challenge problems. There was the one challenge problem where a road was described by a function, and then there was a sculpture was vandalized at a particular point off that road, and we wanted to figure out where exactly precisely was a shot taken from and it was with a paintball gun from a car traveling along this road that it would have hit this point. And so that's one application of derivatives and tangent lines. But at the end of chapter 2, there's plenty of other challenge problems as well. The end of every chapter has a couple. So let's just maybe do a preview of those. In challenge number 3 at the end of chapter 2, it talks about a skate ramp which has a particular profile, which is built up from some different functions that are pieced together in something called a piecewise function. So you can think about the profile of a skate ramp and having fun following curves there as a piecewise function, and then you could analyze that. You could answer questions about how steep it is at a particular point, and in this particular one, the International Federation of Skate Parks states that no park can have a ramp of steepness greater than 10 units per 1 horizontal unit. And so that is translating that English into our mathematical phrase, which would be, what is that asking about? 10 vertical units per 1 horizontal unit. Well, that's a rate of change, that's a slope. And so we want to find out on this skate ramp, where are there slopes that might violate that. So you can use tangents to do that. The next challenge problem, number 4, is actually a murder mystery, and it uses an exponential function, which we're going to learn about in a few videos from now, how to analyze those and in this case solve who did a particular, who did the murder at what time. So we'll be able to use that. And then challenge number 5 is about a satellites in orbit. So it's an elliptical orbit, and there's some docking stations and places where the satellite needs to take pictures directed in a certain, oriented in a certain direction. Again, tangents come into play. And then another example, we're working our way up to what are called optimization or max or min problems, and that'll be at the end of chapter 4. We want to, and this is business calculus, do something like this. We want to find the maximum profit for a function. Someone's described the shape of a function that might describe a business's profit. Maybe it's over time, maybe it's the price of a stock over time, or it could be something we want to minimize cost. And so we want, given a function, to find those extreme values, those max or min values. And we're going to be able to do that all with derivatives. And we'll see a little bit of a glimpse of that in chapter 2. So we're working towards chapter 4, solving these very applied optimization problems, very practical problems. In chapter 2, though, we need to learn ways to find critical points and where a function is increasing and decreasing. So reviewing from chapter 1, remember that a critical point is a place where your function has a horizontal tangent line, which is another way of saying that the slope of the tangent line there is 0, which is another way of saying that the derivative there at that critical point is 0. And then the second thing we learned from chapter 1 is that the slope of the tangent line tells us information about whether a function is increasing or decreasing there. If the slope of the tangent line is leaning this way, is positive leaning, then the function, the derivative must be positive there. And so that information tells us where we're increasing, because you're rising as you're pedaling uphill. And then if the function goes down, it's decreasing, we're pedaling downhill. Therefore, the slope of any tangent line on that section would have to be negative, which means the derivative on that section would have to be negative. And we saw how to do that visually in chapter 1. Now in chapter 2, we're going to be able to do it algebraically and analytically. Okay, so that's setting the stage. And in this particular section, this video, we're going to learn a couple of rules here. We have a toolbox of differentiation. We'll put it over here. When we're done this chapter, we're going to have a handful of what are called differentiation rules, which are just rules to take a derivative, right? And the first ones we're going to learn are the power rule and the constant rule. And then we'll add several more as we go throughout the term. Okay, so we ultimately want to do something like this. We want to find the critical points and intervals of increase and decrease. For a particular function. And maybe we're going to work at this function here. Let's see. All right. So for this particular function, we want to find where are the critical points and where are the intervals of increase or decrease. Remember reviewing from chapter 1, you could put this into a tech tool, pull out a calculator, go to Google, go to Wolfram Alpha, go to Desmos. Graph this thing and you could visually get an idea of your answers for this. And this is a good way to check your work or to start getting some intuition for the problem. Again, critical points are those places where you have a horizontal tangent line. So you'd be zooming out far enough so you could see the whole function, seeing any trends. And then the intervals of increase and decrease. That's just where you're pedaling uphill or downhill. Okay, so that's our goal, but it's going to take quite a bit of work because at this point, the only way we know how to take a derivative is with the limit definition, right? The derivative is going to help us answer both of those questions. And the limit definition looks like this. Limit as h approaches 0, f of x plus h minus f of x all over h, which is really just the slope of secant lines. And then we make the secant lines get closer and closer. The 2 points of the secant lines get closer and closer until we get to take the limit and we have our derivative. But again, the whole point of chapter 2 is to avoid that, to understand it and to be able to see how it came about. But then we want to avoid it so that we can take this derivative in a much easier way. And this particular function is going to be easy to take the derivative using these two rules, the power rule and the constant rule. So I have to show you the power rule. And this is in the beginning of chapter 1, the first couple pages. There's a pattern. So someone was, in fact, the original founders of calculus, Newton and Leibniz, noticed this pattern that when they applied for a function, the function f of x, and then the derivative, they noticed for functions that were power functions, things like this, x squared. So this is like y equals x squared, y equals x cubed, y equals x to the fourth, y equals x to the first. Anything where it's x raised to a power, nothing else, that's called a power function. And they noticed that the derivatives, f prime of x, had this pattern. And then that got them wondering if this pattern was a general rule, and it turns out it is. And so pause the video for a minute and see if you can see the pattern. If your function is x squared, the derivative is 2x. If your function is x cubed, the derivative is 3x squared. And again, remember, they got this after pages of work applying the limit definition each time. So I'm just giving you the answer here, but there's a lot of work going from here to here, from the left column to the right column. And so what we're wondering is, in general, ... for any x to the n, what is the derivative? F prime of x. So again, pause the video, take a moment, see if you can fill in that box. Just take a guess, and then we'll see how close you were. So this is just pattern recognition, the same thing the initial founders of calculus did. And so here's the rule. If f of x equals x to the n, then the derivative, f prime of x, is n x to the n minus 1. and check that that works, right? No matter what the power is. Here, the last one, x to the 5th, I go 5, x to the 5 minus 1 is 4. So another way of remembering this, this is a little phrase from my high school teacher, is times the power down a power. Right, and that's what we did here. If our power function was x to the 5th, we go times the power down a power to get the derivative of 5x to the 4th. And we can use that information to find, again, slopes of tangent lines, equations of tangent lines, critical points, and increasing and decreasing. So the first two should be reviewed for us, slopes of tangent lines and equations of tangent lines. So the next two we're going to learn this time. So again, we're ultimately trying to work our way up to solve a function like this, which has some power functions in it, but it also has this constant, it has these constants multiplied in front. And so we're going to then need the constant rule before we can solve a problem like this. At this point, though, we could do something a little bit easier problem. We could find the equation of the tangent line for, let's make a power function, y equals, let's say, we're going to make it just a power function. No constants yet. Let's just say x cubed at x equals 1. Just to get a visual of what we're trying to do in this example, here's y equals x cubed. We want to go to x equals 1. That's maybe about here, and get the tangent line. Definitely looks like it's going to be a slope of a positive number, and maybe bigger than 1. It looks like, if my graph isn't to scale, but it's definitely a positive leaning line, and it'll have a negative y-intercept. So to get the equation, we have a few pieces of the puzzle. And we know that right here, this is the tangent line. The slope of the tangent line is the derivative. So we just need to find f prime of 1, and that will be the slope of this line, f prime of 1. So before we get f prime of 1, we'll get f prime of x. So y is a function of x, right? They mean the same thing. So I could have written it just like that. So the derivative is times the power down a power. That's the only differentiation rule we know at this point. It is a power function. So we go times the power down a power, and then we evaluate it at 1, and we'll get 3 times 1 squared is 3. So the slope of this line has to be 3. Again, kind of fit what we thought. It's a positive leaning line, looks steep, pretty kind of steep, bigger than 1. Last piece of the puzzle, find the equation of the tangent line, means we need to evaluate this y equals mx plus b and solve for b. We know what m is. That's 3. And now we have to figure out what b is. This, as it's written right now, has 3 letters, 3 in there, and if we just had 1, we could solve it. And so we want to put in a value for x and a value for y, and then we'll be able to solve for b. So what is a point on the function y equals x cubed that we know? There's infinitely many points on here, but there's one we're interested in. The point we're interested in is on the function and on the tangent line, right? We have to be on the tangent line. And that's when x was 1. What is y? How do you figure out the y value? You always, always, always go back to the original function, because y is a function of x, tells you heights on the graph, right? So I'm really just plugging in f of 1, which is 1 cubed, which is 1. So this is the point 1, 1. That lives on the tangent line, and it lives on the function. It's also in our vocabulary the point of tangency. Okay, so I plug in 1 for x and 1 for y. And I see that 3 plus b is equal to 1. B must be minus 2. So then our y equals mx plus b is 3x minus 2. That's our final answer for this example. Does it check? Yes, again, we thought we had a positive steep leaning line. We thought we had a negative y-intercept. The best way to check it would be to pause the video, go to your favorite tech tool, graph both the equation of the tangent line and the function, and make sure they just barely touch at 1. Okay, so there's our first use of the differentiation rule to solve a problem. And the differentiation rule was the easiest rule we have so far, but it's the one we're going to use most often. You will use it most often in your mathematical career. It's the power rule. The neat thing about the power rule, again, you'll see this in the first couple pages in your chapter, in chapter 2, is that the power rule works for lots of other, so there's a page here with the power rule in the box. So we just did times the power down a power. But it also shows that it works for all sorts of other exponents, negative exponents, fractional exponents, decimal exponents. So let's do a few of those just to make sure we're familiar, looking for sort of disguised power rules. So in this chapter and a good bit of your calculus career, you're going to do things like this. Here's a function, differentiate it. So you'll see this instructions often. Differentiate f of x equals, and let's pick one of these. Let's pick, let's see, we said we could have negative exponents, so let's do like this one. Okay, the only rule in our set of differentiation rules, I'm often going to call that your sort of toolbox of differentiation rules. The only rule we have is the power rule. So it has to be that somehow I can like massage this function and make it fit the power rule. So this is why on the pretest, you have to make sure you know your rules of exponents. When x squared crosses the bar, it becomes x to the minus 2. So this is the exact same thing. 1 over x squared is x to the minus 2. X to the minus 2 now does look like it fits x raised to a power, right? It might have been disguised here, but now it's pretty clear. It fits our power rule. So we can take the derivative by going times the power down the power. So the derivative in any x is times the power, and then down a power, subtract 1 gives me minus 3. You can write it like that, or it's the same thing to put it back as a fraction. So now you could evaluate this derivative at any point. I could throw out, 7 different points I'm interested in. Tell me the slope of the tangent line when x is 1. You plug in 1, and you get minus 2. Tell me the derivative when x is 2. Tell me the derivative when x is minus 1. I could throw out as many numbers as I want, and you just function evaluation, but this time you're plugging into the derivative, and each one of these means slopes of tangent lines, and they tell you information about the function. So we know that the that the function is decreasing, because the negative sign, at x equal 1. We know that the function is decreasing also at x equal 2. We know at -1, when x is -1, the function is increasing. Right? So you can interpret those slopes to tell you at precise points where we're increasing and decreasing. But we ultimately want to be able to do something like this, like not just pinpoint particular points and say increasing or decreasing. We want to be able to say over an interval, over a range where we're increasing or decreasing. So we're working our way up there. Again, that's kind of our goal by the end of this one. All right, so we said we can do it. We can do the power rule when you have negative exponents. Well, you can also do it when you have fractional exponents. So let's say I asked you to take the derivative of the square root of x. Again, we only have one rule. We don't have a rule that has square roots, but it has to be that somehow I can massage this function into the power rule. Again, from the pretest, we know that you can go back and forth between square roots, cube roots, any type of root, and its exponent form. And so now it does look like a power function. I can take the derivative by going times the power down a power. Make sure I subtract 1, so that gives me -1/2. Again, okay to leave it like that, or if you want to like sort of pretty it up or a little bit, check maybe another tech tool might give an answer that looked maybe in this form. You might see it in this form. Make sure you can go back and forth, have some familiarity writing it either way. Once again, you could find slopes of tangent lines at any point. You can find equations of tangent lines. You can find CPs. I'm going to get there. Okay, so that was negative exponents, fractional exponents, and decimals, kind of the same thing. think you can take it from there. Okay, so maybe let's do just a couple more before we get to our second rule, the constant rule. So maybe we want to differentiate square root of x over x squared. Kind of combining some things now. So square root of x in this class, whenever you see that, turn it to its exponent form. Now you have to remember a rule from the pretest. This can come up, cross the bar becomes x to the minus 2, but now I have x to the 1/2, x to the minus 2. They have the same base, so I can combine the exponents. And so I'll get x to the minus 3/2. Have I done a derivative? Have I differentiated? No, that was all just work to simplify the function and put it in a form that it fits the power rule. And it does now. Now it is x to raise to some power. Now we're ready to apply the power rule, take the derivative, go times the power down a power. Right. Again, can leave it that way, or you can, if there's some reason to simplify. Okay, one last problem here. No, we'll save this one. Okay, so let's go on to our constant rule. All right, suppose I want to take the derivative of this function. It does have the power part in there, x squared, but it has this minus 3 in front of it. And so now we're ready to get to one of our constant rules. Let's see, I'll show you the page here on your journal where several of these appear. If you like thinking of them, the boxes again are important things on your constant rule pages. But even though it shows like 3 separate things, I think you're going to see that they're so easy that you don't even have to like memorize them or distinguish them, because they just make so much sense. And so the first one is, if you're, and we're going to use the second box there on that page, if you have a constant times a power function, so again, we have like minus 3 times x squared, you're just going to take the derivative of the x squared using the power rule and then multiply it by the constant. So using some notation that you'll see in this book a little bit and sometimes in other classes, d dx is another thing saying take the derivative of x squared. So this is minus 3 times 2x is minus 6x. And I sort of drug that one out a bit, but it's actually another way you can do it is just say times the power down a power, right? So you can kind of skip straight from here right down to the derivative, still using the times the power down a power. So 2 times minus 3 is minus 6x. All right, let's try a few more. And then I think we're almost ready to do the problem above. All right, suppose the function is just y equals 7. Well, what does that look like? Horizontal line going through 7 on the y-axis. And the derivative of this, there's a rule, the first box on that page I just showed you. The derivative of a constant is 0, but let's see, why does this make sense? Because at any point, if I stop and draw a tangent line, the tangent line is the line. Like the little linelet that I would draw if I zoom in and zoom in, the tangent line is the line. And every single time, they have slopes of 0 because the line itself is a horizontal line. So anytime you have a constant and you want to take the derivative, you get 0. That's going to be a really easy rule for us. All right, but what if I had something like this? X squared plus 7, and I want to take the derivative. Well, we're going to actually think about this as, we call this the sum and difference rule, but also it's just so easy, or the addition and subtraction rule, that Again, not really much to memorize on those. They make sense, make a lot of sense. So if my function has a couple parts divided by a plus sign, my derivative will be the derivative of each piece. All right, so now I think we're ready to take the derivative of the one above. The function has really 3 pieces. So the derivative will have 3 pieces. The derivative of the first one, it's our power rule and our constant rule, but you can just think about all in one, times the power down the power. So 4 times -3/4 is -3. Down a power for the exponent. And then the next one, 3 times 1/3 is 1. Down a power gives me x squared. And then the last piece is a constant. The derivative of a constant is 0. All right, so again, we've taken the derivative. That's the piece we're going to need to ultimately do this problem where we find critical points and intervals of increase and decrease. All right, let me do one more, and then we're almost ready to tackle that problem. Suppose our function is x cubed minus x squared plus x minus 1. Okay, now we get to use the difference part of the sum and difference rule. Our function has 4 pieces divided by different addition and subtraction signs. And you can take the derivative of each piece. Power rule, 3x squared. Power rule, 2x. We'll come back to that one, and the last one is 1. Okay, so the third term is x, and we need to take the derivative of x. Well, it actually does fit the power rule, because it's really like an invisible 1 power here. And we can take that times the power, so that'd be 1 down a power. X to the 1 minus 1 is 0. But anything to the 0 power is 1, so this really just becomes 1. And you can think about this third term as its own rule if you want, but again, you work enough of these problems, practice problems for your homeworks, and you'll see this one also makes a whole lot of sense. It's called the linear rule, which is if your function is a linear function, like mx plus b, then it's just the m sitting in front. So I actually had another little invisible 1, right? The coefficient in front of this was an invisible 1. And you can just take the slope. Why does that make sense? Think about a linear function. Y equals mx plus b. No matter how you draw that linear function, anywhere you stop and draw a point of tangency and draw the tangent line is the line. The line has slope m, therefore the tangent line has slope m. So therefore the derivative is m. Okay. Just to make sure we got that. Let's say, can we do this one? 2 square root of x minus 7x plus 4. Okay, before I take the derivative, it's going to help you if you rewrite this as its exponent form. So this is really the exact same thing as saying 2 times x to the 1/2 power. And then I see there's 3 pieces. It's going to have this structure. The first one's times the power down a power, 2 times 1/2 is 1, and then x to the minus 1/2, subtracting. This next one is the linear rule. So any constant times x is just that constant. Last one is the constant rule. The derivative of a constant is 0. Again, remember why you're doing it. It's going to be easy to forget because you're just going to be cranking away, becoming a bit of a human calculator doing derivatives. Remember what the point is. The derivative represents what? It's the slope of the tangent line at any x. You give me an x, I'll spit out how steep you are at that x, right? The slope of the tangent line. Why we ultimately care to do it is we want to do problems like this, where we want to find where are the places where you have horizontal tangent lines, because ultimately those are good places to look for where the function might be at max, maximizing profit. or minimizing cost. So that's our goal. We have to get good at doing this to ultimately do those more interesting problems. Okay, so we'll come back to this one in the next video.